Let's continue with our Chapter 6 review. This is Part 4. Number 22 says, in one game, Janet attempts 8 free throws. How can you use simulation to find the experimental probability that Janet will make 3 free throws in a row? So the key part of this question is that it's 3 free throws in a row, not just 3 free throws. So what you want to do is you want to mark only 3 out of a total of 8 cards. You put the cards in a hat or in something else that you could draw them from. And then you want to do a certain amount of trials. It could be 10, it could be 20. The more you do, remember, the more accurate that your answer will be. And a favorable outcome in this case, because it's 3 free throws in a row, would be if you draw out the 3 marked cards in a row. If you did a trial and you did 20 times where you drew out all 8 cards without replacing, that's the other key part, you would not want to replace the cards, then you will have one time where it happened you drew all 3 out in a row. Your probability that she will shoot 3 free throws in a row in one game would be a 1 in 20 chance. Okay, number 23 says, you measure the width of a classroom as 24 feet 6 inches. How long would you draw this width on a scale drawing if you use the scale factor 1 centimeter to 2 feet? And you want to record your answer to the nearest 10th centimeter. Well, what you would have to do is simply use the conversion factor that you're trying to do. You want to do 1 centimeter for every 2 feet, and you want to figure out how long it would be. Well, your x is the part that you don't know. You don't know how many centimeters long you will show room to be on your paper. You do know that the room is actually 24 feet 6 inches, which is 24.5 feet. I simply will cross multiply and solve. So I get 2x equals 24.5. I divide by 2 on both sides, and I will want to draw a line that is 12.25 centimeters in order to represent my room. Let's look at number 24. Number 24 says, a class finds that the experimental probability for rolling matching numbers on 2 number cubes is 0.21. How much greater is this value than the theoretical probability of rolling matching numbers on 2 number cubes? So what we need to do is look at what the chances are for rolling matching numbers on 2 number cubes. And the chance for rolling matching numbers on 2 number cubes so the way I calculate that, I simply take the chance that roll numbers that are the same, which is 1 out of 6, and I change that into a decimal. It's going to be 0.167. And because the class found that the experimental probability for matching numbers on 2 number cubes is 0.21, the theoretical probability is 0.167. In order to find out how much greater that value is, I would subtract 0.167 from 0.21. So I have 0.21, take away 0.167. And so if I subtract those two, I will have to borrow. So I'm going to borrow all the way from this. This becomes a 1. This becomes a 10. This becomes a 10. 10 take away 7 is 3. 10 take away 6 is 4. 1 take away 1 is 0. So I have 0.043 is the difference between the experimental probability and the theoretical probability. And the last number, 25. A spreadsheet is used to generate random numbers from 1 to 365 to represent birthdays for a group of 23 people. Of 60 trials, 28 include a pair of matching numbers. Using this data, what is the experimental probability that in a group of 23 people, 2 will have the same birthday? So for number 25, the important information that I need to look at is the fact that there was 28 that included a pair of matching numbers. That means that there was an outcome in our experiment where somebody would have a birthday that's the same as someone else's. Simply take the probability, which is 28 out of 60, and that reduces down to 7 out of 15. And if I wanted to put that into decimal form, it would be 0.467. So the experimental probability of 2 people having the same birthday would be 7 out of 15. And that's the end of our review out of the book for the Chapter 6 assessment.